Good morning guys, welcome back in another video of Liceo Ancina. Today we're going to talk about waves. A wave can be described as a disturbance that travels through a medium from one location to another location. The big property of a wave is that it transfers energy without moving matter. There are two categories of wave. It can be transverse or longitudinal depending on the direction of its oscillation. Transverse waves occur when a disturbance causes oscillations perpendicular to the propagation, which is the direction of energy transfer. Longitudinal waves occur when the oscillations are parallel to the direction of propagation. But let's see another type of waves, standing waves.
A standing wave is an harmonic wave that swings as the time passes, but remains stationary in its position. The easier case in which we can see that wave is a string with both ends blocked. Those points become nodes, points of no displacement. The frequency generator could generate frequencies between 1 and 1800 Hz, with a sensibility of 0.1 Hz. Around 10.3 Hz, we have the first harmonic, which is also called the fundamental frequency. In this case, we have two nodes, the two blocked ends of the elastic string, and one antinode in the middle. If we increase the frequency to 20.7 Hz, exactly the double of the fundamental harmonic, we will find the second harmonic. If we triple the first harmonic, we will find the third harmonic, around 31.0 Hz, and so on. Now try to predict the 8th harmonic. F8 is equal to 8 times F1. The result is 82.4 Hz. If we generate a frequency of 82.4 Hz with the frequency generator, we will see that the wave is exactly the 8th harmonic, formed by 9 nodes and 8 antinodes. If we change the tension of the string, the frequency will change. We have a formula. The frequency is equal to the square root of the tension divided by the linear density, all divided by lambda, the wavelength. So, if we increase the tension, the frequency of the harmonic will increase.
Another example of application of these standing waves can be found in various wind instruments such saxophone and flute, which use, to produce the sound, a tube open at both ends, also called open-end air column. The natural frequencies of these instruments can be associated with the pattern of standing waves. In this type of situation, that pattern is the outcome of the interference of a non-inverted reflected wave interfering with an incident wave. In the graphic diagram of these waves, the nodes represent the points at normal pressure, and the antinodes the compression and rarefaction. Furthermore, the number of antinodes will always be greater than that of the nodes.
For closed-end air columns, a standing wave pattern which results is the outcome of the interference of an inverted reflected wave interfering with an incident wave. A standing wave pattern consisting of pressure antinodes at the open end of the air column will be established in the tube. Since there must be an alternating pattern of nodes and antinodes, then the closed end of the tube will always have pressure nodes. This relationship says that the addition of an extra node also means that an extra antinode must be also added to the pattern. There is 1/4 of a wave in any given length of the tube. The formula is length is equal to 1 divided by 4 times the wavelength. So, we have the first harmonic and we don't have the second. We must have the third, the fifth, the seventh, and so. So we have only odd numbers of harmonics when we have an closed-end air column. Examples of closed-end air columns are clarinet and some types of trumpet. Here we go.